Hi students, in a previous lecture we have started the topic from paper number 11, that is solution. In that lecture we have seen the introductory part of this topic and concentration units, both cases, that is temperature dependent and temperature independent units. Now in this lecture we are going to see Rasuls Law, ideal and non-ideal solutions. Now let us see first Rasuls Law. Now before dealing with this Rasuls Law, first of all we should know what is vapor pressure, that means concept of vapor pressure. Now in order to study vapor pressure, consider if suppose we have a liquid and if suppose here we have the solution of A and B component, and here we have the pure liquid. Now at any temperature T, this liquid remain in equilibrium with the vapor of this liquid, and here also at any temperature T the solution is in equilibrium with vapors. Now at any temperature the forward process takes place, that means the molecules in the liquid has tendency to escape from that state and goes to vapor state, and initially the rate of forward process, that means the evaporation process, is high, and afterwards the vapors molecules which are present in a vapor phase condense and drop down in the liquid, and the reverse process favors, and therefore initially the rate of reverse process is slow and afterwards it becomes accelerate, and after some time the two rates become identical, and here we call it as the vapor remain in equilibrium with the liquid here. Now at any temperature vapors are in equilibrium with liquid. Vapors are in equilibrium with liquid. Now here the pressure exerted by vapor at this particular condition is called as vapor pressure. Is called as vapor pressure. As here we have pure liquid, then this vapor pressure is called as vapor pressure of pure liquid. Vapor pressure of pure liquid. Now in this case, here vapor are in equilibrium with this solution. Now here the pressure exerted by vapor at a particular temperature at equilibrium condition is called as vapor pressure of solution. Vapor pressure of solution, or you may call it as the observed pressure. You may call it as observed pressure. Here we have pure component and here we have mixture of two components, and therefore here we measure total vapor pressure, and here we measure the vapor pressure of pure component. Now another thing is, what is partial vapor pressure of the component? What is partial vapor pressure of the component? Now here with the static method we can determine vapor pressure of pure component A. Here with the static method we can measure the vapor pressure of the solution. Vapor pressure of solution, the total vapor pressure P. Now here what is vapor pressure of A, what is vapor pressure of B, we cannot determine with the help of experiment. That means with the help of the method. Because if you want to determine vapor pressure of A, then we have to isolate A first. That means we have to make partiality with any one of the component in order to determine vapor pressure of that component. And therefore, if you want to determine vapor pressure of individual component of solution, then it becomes the partial pressure. If we measure vapor pressure exerted by A vapors, then that is called as partial vapor pressure of A. And if we measure the vapor pressure of B component out of this total, then it is called as partial vapor pressure of B. Now with the method, it couldn't be possible. That means in presence of both the components, we cannot determine vapor pressure of individual A or individual B. And therefore, in order to solve this problem, or in order to find the answer of this question, Rasuls gave solution for that, and he introduced his law, that is called as Rasuls Law. Rasuls Law of partial vapor pressure. Now, this law can be stated as the partial vapor pressure of any volatile component of solution is equal to the vapor pressure of pure component multiplied by mole fraction of that component in solution. Mole fraction of that component in solution. Now what it means? We have a problem that how to measure partial vapor pressure of component in solution. Because with static method we cannot determine the partial vapor pressure. We can determine the total vapor pressure. And to solve this problem, Rasuls stated his law, which is called as Rasuls Law, and according to that law, the partial vapor pressure of any component of solution. Suppose we have the solution of A and B, and here we determine the total vapor pressure. The total vapor pressure. If we take individual component A, individual component B, then here we measure the vapor pressure of pure component A, vapor pressure of pure component B. And if we have this particular solution, and in that solution, if we mix these two components, Na moles of A and B moles of B, then mole fraction of A in this solution becomes Xa, and mole fraction of B in this solution becomes Xb. Now, the partial vapor pressure of A for this in this solution becomes Pa, and for B is Pb. Now, to determine the partial vapor pressure according to Rasuls law, we can write the vapor pressure of pure component A into or multiplied by mole fraction of that component A. Similarly, partial vapor pressure of B is equal to vapor pressure of pure component B multiplied by mole fraction of B. Now this is Rasuls law. Partial vapor pressure can be determined with the help of Rasuls law. Partial vapor pressure cannot be determined directly by static method, but it can be determined with the help of this Rasuls law. Now, according to Dalton's law of vapor pressure, the total vapor pressure, if suppose the vapor behave ideally, then according to Dalton's law, the absorbed pressure, that is total pressure, is equal to sum of the partial pressures of the component of solution. Sum of the partial pressures of the component. And therefore, absorbed pressure can be calculated as P0A XA plus P0B XB. And this is all about the Rasuls law. Now, according to Rasuls law, solutions can be divided into two types. That is, ideal solutions and non-ideal solutions. Ideal solutions and non-ideal solutions. Ideal solutions and non-ideal solutions. Now, what is ideal solution? Ideal solution. A solution which obey Rasuls law at all concentration and temperature condition is called ideal solution. A solution which obey Rasuls law at all concentration temperature condition is called as ideal solution, or you may call it as perfect solution. Perfect solution. And what is non-ideal solution? A solution which does not obey, solution which does not obey Rasuls law at all concentration and temperature conditions is called non-ideal solution. Solution which obey Rasuls law at all concentration temperature is called as ideal solution, and solution which does not obey Rasuls law at all concentration temperature condition is called as non-ideal solution. That means ideal solution obey Rasuls law at all conditions, where non-ideal solution does not obey Rasuls law at all condition. And at some condition it may be obeyed, but entire condition this law cannot be obeyed by these solutions. Now we can distinguish ideal and non-ideal solutions with the following points: ideal, non-ideal. The first difference is ideal solutions obey Rasuls law at all concentration temperature conditions. Now here it does not obey Rasuls law at all concentration and temperature condition. Second difference including point. Now here during formation of ideal solution, no heat evolve or absorb. No heat evolve or absorb. In this case, there may be evolution or absorption of heat during formation of this solution. During formation of this solution. Third difference, the total volume of solution is the sum of the volumes of the component of solution. That is, V is equal to VA plus VB. V is equal to VA plus VB. Here, total volume may not be equal to sum of the volume of the components. That is, V is not equal to VA plus VB. The total volume may not be equal to sum of the volumes of the component. That means V is not equal to VA plus VB. But here total volume is equal to the sum of the volumes of the component. Suppose VA is the volume of A component, VB is the volume of B component, then sum of these two is equal to total volume of the solution. But here the sum of the volumes of component not equal to total volume of solution. And last differentiating point, that is fourth, the total observed pressure is equal to sum of the partial pressures of the component. Partial pressures of the component. Here, that is P is equal to PA plus PB. Fourth, the total observed pressure may not be equal to the sum of the partial pressures. That is, P not equal to PA plus PB. Now, for example, ideal solution is ideal benzene toluene system, and here any system, that is ethyl alcohol water system. Ethyl alcohol water system. Now, with the help of these 5 points, we can distinguish the ideal and non-ideal solutions. Now, in next part, we will see the vapor pressure curves of ideal solutions for miscible liquid pairs. Okay, thank you.